So hello there, my name's Matt Turner and I'm going to be talking you through software networking and network interfaces on Linux. I'm originally a software engineer, but for the past 5 years I've been doing DevOps and infrastructure work, and that's taken me very close to the network and to the systems layer and the internals of modern Linux systems. And when you get close to this stuff, especially if you're looking at VMs, containers, Kubernetes, Istio, you'll find that there's a lot more to networking than ETH0. Learning this stuff has been very valuable for me in terms of debugging and understanding the systems that I've been working with, and I hope it'll help you in the same way. So let's dive in. So we'll start here with a very simple diagram of a host, a computer if you will, either a physical one or a virtual machine, and that's the grey box. The simplest type of network interface is this blue arrow that comes in from the outside. This is your classic ETH0, or today this would have a name more like ENP0S2. These devices are now named after their position on the bus. This is more of a BSD style name, so EN means it's an Ethernet adapter. P0S2 is sort of bus 0 slot 2. But oftentimes these used to be called ETH0. If you added a second one, it was called ETH1. As I say, this is your most simple kind of interface that takes network packets from the outside world and brings them into your system. The first thing I want to talk about is the arrow on the end of that interface. That's something I've drawn. And in the model that I'm going to present to you, everything that is dangling, and every spare arrow on one of these interfaces can be used. It can be used to send and retrieve packets. So we'll see cases, where these arrows are sort of subsumed. The interfaces are plugged into other systems. So if you think of this as sort of a male component, then there are certain female components that they can interact with. But any sort of dangling arrow like this can be used in my host. And in order to use it, I have to assign it an address. So here we go. I've put on an IP address. All right, a very simple. This is a private range, Class C private range, 192.168.0.10. This interface has now been brought up. It has an IP address, and I can use that interface now to talk using the Internet Protocol, right, IP, to other machines, whatever might be on the end of that blue wire. So what can I do with this? The first thing I can do is make connections out. So here I have this green box is a process, a user space process in my system, and it's connecting to google.com, right? It wants to send ping packets to google.com. Maybe, or if it were a different program, it might want to send TCP packets and get a reply and actually download the website that's hosted there. So this connects through my interface, and the source address of those packets is 192.168.0.10. On the flip side, I can make the system call bind, and another user space process, maybe Nginx, which is a well-known web server, can receive packets. And in this case, it's a web server. It'll make replies, and those involve sending web pages to the client. So this binds to our address, to our interface. Technically it binds to the address, and the address tells it which interface to actually sort of activate and to start listening for these packets. In this case, this isn't a valid invocation of bind. It doesn't take a string, it takes a different data structure. But what I'm showing here is that actually in this case, I've asked it to bind to port 80 on any IP address. And because there's only one IP address in this system, on this one interface, then I am bound to 192.168.0.10, and any packets that come to port 80, down that wire, are going to get sent to my Nginx by the Linux kernel and its networking stack. So, how can things get more advanced? We've really done the simple bit, right? How do things get more complicated from here? So the first thing I can do is add a second address to the same interface. This is entirely possible, entirely okay under some circumstances, but it's often forgotten, so it's worth putting in here. So this IP address I've given here is from a different one of the private ranges. This is a Class B private range, 172.16.0.10. It is not okay for these two addresses to be on the same network, within the same subnet, right? So I couldn't have 192.168.0.11 on this, because a lot of things will get very confused. But with this being on a separate network, that's actually fine. And our call to bind to port 80 on any interface means that actually Nginx is now listening on both of those addresses, but the packets are expecting to be coming down the same wire. As I say, not actually very common, but it is possible, and there are reasons why you might want to do it. More common is to have a second interface. If this were a physical machine, this would be realized by actually having a second PCI network card plugged into your system. This was very common for all these sort of server-grade hardware, maybe for extra bandwidth, maybe for redundancy, or maybe just for connecting, as in this example, to two different networks, right? So maybe 192.168 that Nginx is listening to is your sort of internet-facing interface, and then ETH1 is plugged into your management switch or your sort of network internally. So that's on a different network that has a different address, and maybe SSHD would be listening to that. Nginx, you'll notice in this case, is only listening on one of those addresses. It's only bound to one of those addresses because that address is specified when we made that bind system call. Equally, bind can specify the other address, and it'll then be taking packets off that other interface. Any packet that hits, that comes down that ETH1 wire with 172.16.0.10 as its destination address, will be picked up by the Linux kernel. Other than anything else without one of those addresses will be dropped on the floor. That packet will be picked up and it'll be delivered to the Nginx user space process where it can do something with it. So what is an interface? An interface is quite literal in the classic sense of a sort of a meeting between two things. This is also called a network adapter. So this interface is the interface between the inside world and the outside world. In this case, I'm showing an E1000, which is a model of Intel gigabit network card. So this would be a PCI network card, probably, and it interfaces the world of the software, the Linux kernel within this grey box, with the network cable on the outside. One of the reasons it's called an adapter is that often that's what these things used to do. So they would adapt, they would transform one type of network into another. So your network could be Ethernet, or it could be ATM, or it could be fiber channel, it could be InfiniBand, it could be any of these types, represented, for example, by this circle on the left-hand side of this. So this is let's assume an Ethernet network, and this E1000 device adapts that. It interfaces that Ethernet network to the sort of software abstraction within the grey box, and that's something that we'll see is quite important. It's no longer there are certainly cases where interfaces within the host lose a lot of the attributes of the sort of network that they're actually connecting to. So they're all standardized. Equally, I could have a fiber channel wire plugged into this machine, and there would be this adapter, which would not only do physical adaptation, it would terminate whatever form of electrical signals or optical signals that uses. It would understand basic things about sort of start and stop bytes and sort of flow control down that cable, and give me a nice sort of buffered packet-based interface. So let's think about what that E1000 is in this case. Well, it's a block of hardware. It's a physical PCI device that's plugged in, and it's a driver to make that work, because each one of these things obviously has different control signals that need to be sent into various registers and whatever to actually make it work, and that's manufacturer specific. But those drivers are just a bit of software. I mean, there's actually a bit in the middle called the firmware. Anybody who's familiar with the term firmware, you get the joke that it's firm because it's halfway between hard and soft. So in this case, this thing will have a firmware that actually understands how to, use the transducers on this PCI card to raise and lower voltages or to flash LEDs, and then the driver is the piece of software that tells that firmware to do that, probably using writing to registers and raising interrupts and so forth. But this driver, this higher level piece of software, understands how to make the blue arrow on the inside of this box. This thing is an interface. It has a name, and it can take IP addresses, and that functionality is the same no matter what make and model of Ethernet adapter we've got. And in fact, this ability to take an IP address is the same no matter what kind of network adapter we've got. The fact that it's Ethernet means that it has another type of address, the Ethernet layer address, the MAC address. We'll come on to that. But what we have sort of on the inside within this yellow box, and I want to labor this point, is that this is a sort of network interface thing in the Linux sense. This is not the hardware directly. This is an abstraction over it, right? So we think of that blue arrow as a dangling RJ45 if you want, but it's abstracted away from that sort of hardware. So yeah, let's look a little bit closer at that concept. So imagine we have another type of interface, right? I want another network interface This one is an ETH1, though. This one isn't backed by a PCI network card. This is just a foo0. It takes packets from somewhere and it delivers them. It has this dangling blue arrow that I can do something with, I can give it an IP address and I can connect through it, or I can listen to it. But that interface doesn't have to take packets from the outside. This interface doesn't have to interface the outside world to this generic dangling blue arrow thing to which I can assign an IP address and send and receive packets. It could be backed by something else. So for example, it could be backed by another green box, just a user space program. So something that makes system calls into the kernel to tell it to pretend that there's another interface in the system, and then to sort of punt packets in and out by writing to a piece of memory that it's sharing with the kernel. It's actually not very difficult to write a C program that does the bare minimum on this regard. So we're calling this thing for now sort of packet D, the packet daemon. So it's a long-running piece of software that acts like an actual network card would. So it can say, hey, I've got a new packet, just like the E1000 does when voltages actually twiddle on the wire, but packet D can sort of make that up. And equally, it can be sent packets through foo0 and it can do whatever it chooses with them. So as I say, this thing can be given an IP address, say this is now 172.16.0.10. And you'll notice we've changed its name to ton0 because there's a name for this type of interface, which is, if you will, a virtual interface, an interface that's not backed by actual hardware, but is instead backed by a user space process, and that's a tunnel. So now we can ping 172.16.0.10, and the result of that, when ping makes the connect system call or whatever it does, we're not twiddling LEDs or voltages on a wire. Instead, the contents of that packet in memory is being delivered into the program packet D. Packet D is being woken up and given this array of bytes, and it can do whatever it chooses with it. It's, as I say, it's not hard to write a C program. It's maybe 100 or 200 lines that makes the right system calls to receive those packets, to extract the sort of raw IP information, to recognize an ICMP echo request, which is the sort of the ping payload, and then to craft a suitable ICMP echo reply, which is the PONG, if you like, the reply to a ping, such that the ping program says, oh yes, I got a reply and it took 1 millisecond. So what are tons used for? Very commonly, originally they were used for VPNs. So this is what a VPN might look like. Say I want to connect to machines back in my office from a coffee shop. Right, I make a connection to a 192.168 address, and the kernel chooses the right interface to get the packets there in its route table. So if I want to talk securely to the office, then maybe actually I would talk to a 172.16 address. What packet? Those packets go to packet D. What's packet D going to do with them? Well, actually, it's going to encrypt them. It's going to wrap them in an outer envelope, which means they don't travel unencrypted over the internet. They can't be read, and it will then send them to 192.168.0.10. And as I say, the route table will know that the 192 address goes out of ETH0. So when packet D uses 192 address to get directly to the internet, but everything it's sending is actually just a wrapped encrypted version of things that were sent to 172.16. So as far as most processes on my system are concerned, the default way to the internet, the default route is via 172.16. So this is a very classic way. Packet D in this case is a VPN client. This is a very classic way of doing things. And my connection to the internet now isn't that ETH0, it's ton0, and it does what it says on the tin. It puts the packets I send it into a tunnel and then sends them out. There's other ways I can get packet D connected to the internet. All right, it doesn't actually have to send the packets in a tunnel itself. I can set up network address translation. This is a slightly different example to before. This is where packet D wants to talk to the internet. How does it do that? It's just got this dangling ton, right? It's got this dangling blue arrow, this mail thing that, as I said, can be assigned an address. And I've got ETH0, so we've got two mail things. We can't plug them together, but they do both have these IP addresses. So I can set up network address translation, which means that whenever packet D sends things out of its 172.16 address and they're aimed for the internet, the kernel can say, oh yes, well you're just dangling, you're not on the internet, you're within this host, but what I'm going to do is I'm going to rewrite that packet. So I'm going to send it out of the E1000 out through ETH0, like you probably wanted because you wanted to get to the internet. But its source address can't be 172.16 because that's in, if you look at this diagram, that's in this host, and it doesn't mean anything to the outside world. There's no way we could get packets back. So I'm going to swap out its source address, use the 192.168, send it out of ETH0, and then when the reply comes back, I'll remember what I did, and I'll take the 192.168 that it's addressed to, which would get it to anything that happened to be listening bound to ETH0, and I will change that destination address, and I'll put 172.16 back in, and then it'll go back down the ton0 interface and end up in packet D. So this is a way to we're starting now to see internal systems with their own networking that's just virtual, that's just a figment of the sort of kernel's imagination, and we're now getting them connected to the internet. The other thing I can do is actually route this, so I can take the packets coming out of packet D, and I can turn on IP forwarding, and I can say, well, you were trying to get to the internet, say 1.2.3.4, fine. You've dangled into the ether inside this host, but this host knows where the internet is. It knows it's connected out of ETH0. So I'm simply going to forward it. I'm going to take the packet that's sort of ejected out of ton0 and had nowhere to go, and I'm going to stuff it into ETH0 and send it through that E1000 to the internet. So I'm going to forward it on to you. It's like, the kernel is a mailbox, and it says, thanks packet D, you gave me a packet, and I'm gonna do a post redirect. I'm going to cross out the address and put a new one in. Well, not even in this case. That's more like NAT. It says, yes, I know where that person lives. You got it to me, but I am the postman. I know where everybody lives. Let me take care of that for you. It's like putting it into a post box, I guess, would be a better analogy. The difference between this and what we saw before, NAT, is the network address translation, is that there is no translation of addresses. So the packet from packet D goes out onto the wild internet with 172.16 as its source address. Now here we're using private network addresses for everything, so this system actually would never work. But if this thing had a public address, an address that's allowed to be seen on the internet, you still wouldn't get the replies, because the things on the outside, the things upstream of that E1000, ETH0, need to know where to send the packet to get it back. So they know that 192.168 is the sort of address, if you like, of this machine. This is very classic. I get an address on ETH0, and that's what I use to talk to the internet. And obviously, packets can come back to me. 172.16 or whatever that would be, even if it's a viable internet address, nothing knows it's there because it's not on ETH0. So this is where I'd have to use something like BGP to advertise the fact that this address also, this 172.16 network, is also sort of is within this machine. And this is how the wider internet works. So imagine that ton0 is actually an ETH1 poking out of the back. This is exactly how a router works on the internet. It says, hey, wider internet, I have 192.168, you know how to get packets. For that, to me, and indeed that's what my Nginx and things are working on, but I'm actually a router. I've got two entire network interfaces, and behind me, if you will, is this whole other network. I am the gatekeeper to this other network. So you can send things for 172.16 ** to me, and I will act as postman, and I will get them to the right place. Those things no longer have to be on a separate physical network with an actual ETH1 sticking out of the back plugged into them. They can be a figment of this machine's imagination, and you just advertise them with BGP in the same way. So remember what I said. E1000 is an Ethernet interface. So it actually has a MAC address as well. That's not actually shown here, but MACs are the Ethernet level network addresses. They use a slightly different form. You see here six double hex characters, and they're normally rendered separated by colons like this. That ton used to be a tunnel because that's a sort of IP is the internetworking protocol, right? The internet protocol. So that's about getting packets to the other side of the world through through tunnels and whatever. Ethernet is just for local networks. But if I change that ton to a tap, then I can also, so that ton was sort of abstract. That was an IP only interface. That's what I said about it being abstracted away from the underlying hardware. But I can make this virtual interface pretend it's an Ethernet interface as well, right? So it's still virtual. It's still a figment of the kernel's imagination, but it's also implementing that slightly lower level set of attributes. It's pretending it's backed by something that understands how to speak Ethernet specifically. So we're exposing, lower level network details. So this tap can now take a MAC address. So we saw network address translation, which replaces the source IP address of a packet. We saw IP forwarding. These are both IP level, Internet Protocol level things. If my tap can take a MAC address and can be an Ethernet, a virtual Ethernet interface, then I can do Ethernet style things with it. Specifically, I can plug it into a hub and I can switch it. So the next thing we're going to see is this BR0 device, which is a Linux bridge. So this is a virtual bridge, is another name for switch, basically, and this is a virtual switch, again implemented in software, just like TAP0 is an interface implemented in software with no hardware behind it. So I'm sure everybody knows what a physical switch looks like. It's got a whole bunch of sockets that you plug probably RJ45 Ethernet cables into. I've got a virtual switch here that's got a bunch of holes in it that I can plug these dangling arrows in. So if you like, this is the sort of female part. So I can go ahead and I can plug ETH0 and TAP0, which remember now are both acting like Ethernet interfaces. I can plug them into this virtualized Ethernet switch. So packet D can now talk to the outside world because it's on the outside network. This maybe was the way we could have come at this explanation for the start, and then build it up to the IP stuff. But I think the IP stuff is simpler prima facie. The interfaces just have IP addresses, but then in order to get stuff in and out of the machine to the outside world, you actually have to do inter-networking stuff, right? Packet D was sort of its own little network. The E1000, whatever it's plugged into, was another network, and you actually had to route between those networks like an inter-networking thing. And TAP0 then could have been a virtual ATM device, and you are actually routing, right? This is what the internet was for. It was to plug together. The idea of IP was that you could plug together different types of network with different addressing schemes. ETH0 has MAC, TAP0 maybe was ATM and had the ATM addressing scheme. IP normalized all of that, and that's what these virtual interfaces do. But if we take it down a level and give TAP0 some Ethernet attributes, then we can plug them both into this bridge. And as I was saying, Packet D can now talk to the outside network because it's on the network, right? No longer do we have to sort of forward it for somebody. Packet D is now on the network. Much like if you have a network in your home or your office and you've got a bunch of computers on it, if you take a new device and you plug that in with a cable to the same switch, it's now on that network, right? It doesn't have to port forward in from the outside through your router. It's not on a different network and it's not inter-networking. It's actually now on that network. So I've extended the network that, imagine the E1000 is plugged into a physical switch. There's a bunch of other physical computers on it in a star shape. I've now extended that network into my machine and onto Packet D. So anything that gets broadcast on the outside network, those broadcast packets hit the E1000. Software can see them on ETH0, and also Packet D will now see them because the actual true definition of an Ethernet network is a broadcast domain. As in, a network is the expanse of the set of machines to which a broadcast packet will reach. Because if you think about it, you can plug more than one switch together. You can get these sort of multiple stars. You get this connected tree of devices, and a broadcast that's dropped out of an interface by any of them will hit all of them. So that's the sort of the best definition of a network. So as I say, it's like I've plugged another switch into the upstream switch. Except it's not physical, so hence we're sort of talking about virtual networking here. So yeah, Packet D, because it has a tap and not a ton, and it's what it's now being given by the kernel are Ethernet frames, not IP packets, so it has to parse and understand those as well. Packet D can now talk at layer 2, so it could now do Ethernet only things, lower level things. It could send a broadcast. It could, for example, broadcast for DHCP lease. It could respond to ARPs. And as I say, to get in onto the network, we no longer have to mess around with NAT or forwarding or any of those layer 3 things that are more internet style terms. But note that these two blue arrows now aren't dangling. So they've been plugged into this bridge. They've been sort of subsumed by it almost. So it doesn't make any sense to assign them addresses. We can't do that. What would it mean for ETH0 to have an address? Nothing can listen to it, nothing can connect through it because it's being used by the bridge. Both of them can't sort of be sending packets down there. That doesn't really make any sense. If I have an Ethernet cable, I plug it into one machine, I can't plug it into another machine. So yeah, we're a bit of an impasse here. What do we do? Well, this machine actually has nothing dangling now, so nothing can take an IP address. Nothing in this machine in air quotes can't get an IP address because there are no free interfaces, no dangling interfaces that can get an IP. So really, it can't communicate with anything. Packet D can definitely can pretend to have an IP address and can send things. The only thing that can send things in and out through the C1000 onto the outside network is Packet D, right, or whatever else is on the end of that tap. Luckily, to solve this, all bridges have a port. This is called the this is called the host port. I kind of think of it as like an implicit port. So every time you use BRCTL to make a bridge, you implicitly always get one of these interfaces, right? It's called a port. So yeah, they called it a port. It's more like an interface. Imagine, that there was a hole that we found in this thing to plug ETH0 in. There was a hole we found to plug tap in. Imagine there was another hole, and we took a length of Ethernet cable and we plugged one end into the bridge, and then the other end is left dangling. This is now this dangling arrow. So yeah, it's like we took a physical switch and we plugged another cable in, and now we have another end that we can use to host something up. But because it's dangling, because this is all virtual and it's dangling in the host, what that means is we can assign it an IP address and we can use it. So I've now essentially got my original host networking back, right? I've got this. I can give that the 192.168.0.10 address. Nginx can bind to it, ping can connect through it, etc. So I've now basically got my host on the network, if you will, because there's this dangling interface with an IP that I can use to communicate, and Packet D is also on the network because it can send and receive. It can believe it's got any IP address it wants. It can even, as I say, because it's Ethernet, it can go and DHCP broadcast, and it can get a valid IP address that the rest of the network is happy for it to use, and it's then 200-300 lines of C to do basic things with that interface. One thing to note, and I lost a lot of time to this when I was early on trying to debug these systems, is that this bridge interface, this bridge port, the black BR0, has the same name as the bridge itself. This was infinitely confusing for me. If you do an ifconfig or an IP link list, an IP address list, you will see something called BR0. That is not ifconfig being helpful and showing you the bridge, because the bridge is also a network device. That is an interface, right? ifconfig, IP link list will show you the BR0. That is this bridge port, as they call it. That is this spare interface that's implied by the bridge that can take an address. You're not seeing the bridge. If you want to see the bridge, manage the bridge, interact with the bridge, there's BRCTL for that. It's very different. As I say, it always has the same name. You might think they could have maybe called them, a bridge and then bridge interface or something. I don't know. But both the bridge or virtual switch and the interface itself are called BR0. But they're different kinds of thing. They exist in kind of different namespaces, and it's a different tool to interact with each one. It's worth pointing out that the Linux bridge is more than just one of those like female to female RJ45 couplers you get. I think sometimes the term bridge is used to mean a degenerate device that literally bridges two networks. Only has two interfaces. It can have only has two ports. Sorry, it can have as many ports as you want. It's a switch rather than a hub, or that's I guess the other use of the term bridge. It does MAC address learning. It doesn't spam every packet everywhere. It remembers which one should go where. It supports actually STP, the spanning tree protocol. It does quite a lot of stuff. It's an implementation of a sort of semi-managed switch that you might actually pay a few $100s for if you were buying a physical one. It's also not the only option for a virtual switch. We've changed the name here to OVS 0. So another major implementation is what's called Open vSwitch. That's a separate piece of software that you load into your system rather than what I've been calling the Linux bridge, which is a built-in kernel feature. It has a few more features, especially its ability to take its configuration for the way it acts from a control plane. It essentially has an API where you can program in some of the things it does, like port filtering and whatever, the kind of stuff you do with SNMP on a physical switch. The other official option for doing this kind of thing, for plugging layer 2 networks together, is a thing called MAC VTAP, of which more later. So this is kind of a top-down view of the system. This almost looks like a plan, like we've taken the lid off. And the kernel is this big grey sea, everything within this grey box that everything kind of swims in. If we looked at this from the side, we'd see all the layers of user space and kernel space stack. So if you imagine flipping this thing through so that bottom grey edge is kind of towards us, that E1000 box, that OVS box, they're very low level. The E1000 is at the bottom because it's a piece of hardware. We said there's firmware on top of that, there's a driver on top of that, and then there's all these pieces of software on top of that. So in order for something to come in the E1000, get processed, get understood, get across to the OVS, go all the way sort of down through its implementation of IP and its implementation of Ethernet into the piece of code that actually then moves the packet to another one of these ports, and then back up and out, and then across into packet D and whatever, is not particularly quick. You can imagine it, if this thing had a 3D relief, you can imagine this packet going up and down as well as left to right. So this isn't particularly quick. As a result of that, there's been various efforts to make this whole thing quicker, because it turns out this kind of virtual Ethernet bridge is something that people want to do a lot, and they often want to do it in, when they're making their own routers, so when they're doing big internet stuff or telco stuff, and they want it to be very, very quick, very high bandwidth and very low latency. So there's been various re-implementations of the bridge or OVS that actually bypass big bits of their network stack. Examples are Snap Switch, NetMap Veil, etc. So what these things do is, as a packet goes left to right, they don't have to go up and down so much. The difference is that you are bypassing the network stack, so you don't get any of its features. Currently, any of these interfaces, even though they've been subsumed, any of these places where any of these arrows or any of these holes, these ports, can all have IP tables applied to them. Monitoring, logging, filtering, redirection, rewriting of parts of the packet. There's flow control. As I say, OVS implements the spanning tree protocol. All of that stuff, if you start to throw it out, you get fewer layers of software, fewer lines of code to traverse, and things do get faster. As an aside, actually, a lot of Cisco switches, even the bigger ones, are Linux. They are just a Linux kernel running on hardware, but most of the work happens way down in the kernel space, even in the top half of an interrupt handler. So they don't, there aren't these layers and layers of software. Everything is very specialized paths that cut left to right at a very low level and never come up and back down again. You can also take over from vSwitch and accelerate it with a thing called DPDK. You can use SRIOV network interface cards. So that's essentially one of those E1000 blue boxes that has more than one of the blue arrows coming out of them, and they map onto different PCI express virtual functions. It all gets very, very complicated. That's a whole nother talk. Maybe I'll do it one day. But now we know how to use this bridge, and we know how to make a tap interface, which is an Ethernet interface almost, or at least the software abstraction of one, not backed by a driver and a piece of hardware, but backed by a user space process. And we know how to put that onto the same network as the thing that our physical grey box is connected to, right? As if we ran another wire and we plugged it into another machine. We now know how to keep that host, how to get an IP address that is an interface that is floating within the main host, and how to give that an IP address that we haven't cut anything else in this system off from the internet. What can we do? I had that thing called Packet D, and it was basically on my network, in the precise meaning of networks and not an internet. It was on my local area network. It got broadcasts, etc. It can do anything that any physical machine could do. Can I then do anything more interesting? Well, what if I take that user space process, Packet D, that, as I say, was maybe 200 lines of C that, recognized, just did a brutal match to recognize a ping request and reply with the ping response. Maybe I replace that with a virtual machine, replace that with QEMU and KVM acceleration, which is a very big piece of software that can emulate an entire computer of its own and run an entire operating system. So what I have now is another machine, right? I have another one of those grey boxes. And this VM is now on the network, just like Packet D was. So within this green box, which is a user space process, I've got a bit of the code in QEMU, which is interfacing with that, interacting with that network interface. It's taking the packets, and what it's doing with them is it's actually emulating another E1000. So I've got an inside grey box. That's another kernel. That's another instance of Linux. That's a whole operating system. It boots. it blinks into life, it looks around, it sees hardware. All of that hardware is virtualized. It's all emulated. It's all pretend. But it sees what it thinks is a storage controller and maybe even a monitor or something, and it sees an E1000 network card. But when its E1000 driver talks to that thing that it thinks is an E1000 network card, it actually isn't. It's actually a piece of QEMU software that's pretending, and it takes the Ethernet frame that the inner grey box wants to send to the wider world, and instead of raising and lowering voltages on a wire, it just hands it off, to the tap device, and then it ends up in BR0. So it goes down a fake wire into a fake switch. Well, fake's the wrong word. Emulated. And as we say, this is a layer 2 connection because that's a tap, not a ton. So this VM can boot up. It can do a DHCP request. It'll get an address from the upstream DHCP server. All of this happens at the Ethernet layer because that's how you assign IP addresses, which obviously you need before you can start doing IP stuff. And it can get itself, in this case, the network's given it the next available address, .11, and it's now on the same network and on the internet through the same upstream gateway. So that's the more interesting thing you can do with a user space process connect to one of these taps. It turns out that's actually very inefficient, right? Because the bridge and the tap are pieces of software. Really, all they care about is an Ethernet frame, maybe 9,000 bytes worth of data that are an IP packet. Well, are the Ethernet header and trailer, and then an IP packet inside that. And what QEMU was doing recently, though, previously, was having to emulate an entire E1000. So this driver thinks it's trying to twiddle voltages on a wire, by putting things into registers and raising interrupts and all of this stuff. But actually, it's completely fake. So it would be sending the packet a byte at a time. Imagine this were a very simple network card that were being emulated. The driver writes 1 byte into a register on the PCI card over the I/O bus. It raises an interrupt to say there's something, and then on the real card would take that into a little buffer and get it ready. And then the driver puts the next thing into the same register, raises the same interrupt, and it's copied out, and then eventually it puts a special control character into a different register and raises the interrupt and says, right, you can send that now. That's the whole packet. All of that's, a modern driver isn't doing anything that bad, that inefficient. But it's certainly not great to emulate, hardware. So the packet has to go all the way down to a piece of emulated hardware, and then QEMU just unpacks it again. If the thing inside this inner grey box knows that it's being virtualized, knows that it's a virtual machine, then it can just sort of hand that Ethernet frame straight off, and that can be much more efficient. And that's called para-virtualization. Where the OS is virtualized in some ways, but it knows it's virtualized. So there's some disadvantages to that, like the OS has to be capable of interacting with that environment. But the upside is that a lot of things can be a lot more efficient because that environment, when the kernel boots up and looks around, it doesn't see on its fake PCI bus, it doesn't see an E1000 type device. It sees a type of device called a VirtIO net. So it sees a network an alleged PCI card, but it knows actually it's just a fake software device, and its driver for that interacts at a much higher level and is much faster, because you don't have to deal with any of the realities of interacting with hardware underneath. But emulation, virtualization, hypervision, para-virtualization are a whole nother talk. But VMs, they aren't really hip anymore. What do we want to put here on the right now in place of this green box? Of course, we want a container. So this is our orange box here. Well, how do I get that container on the network? Remember that a container is just a chroot on steroids, really. It's a set of user space processes. There's no emulator running. There's no kernel behind them. No separate kernel. That wouldn't make any sense because it's running on the host kernel. So they're just Unix, Linux user space processes, but they're running in a special context, in an isolated context. So how do I get them on the network? Well, this orange box is actually several isolation mechanisms. Lots of different things are isolated. Remember that I said that the sort of right-hand half of that E1000, the old yellow box we had, was software. There gets a point on top of the driver where everything's standardized, and that ETH0 blue interface, blue arrow, really is a figment of the kernel's imagination. And it's the same for every device driver, whatever type of network card that is, they are all required to talk the same language, so that you get the same Ethernet interface, sort of software interface on the inside. Well, we know that software can make interfaces. Drivers can. The driver that runs the E1000 can do all the things it needs to do to tell the kernel that there's an interface, and it can deliver packets in and out of it. But we can also use software to make other kind of virtual interfaces as well, like the taps we saw and the tons that we saw. Well, there's one more type, and it's called a veth pair, or a veth pair, a virtual Ethernet pair. And like I was saying before, this orange box isolates many things. One of those things that it isolates is network, the software side of networks. If you think of eth0 as being actually a standardized software thing, anything within this orange box, the ping and the nginx processes, they can't see eth0, right? So if they make whatever system calls, it is to list the network interfaces to try to see if there's anything they can bind to or connect through, or if they happen to know the IP address that BR0 has, and they try to bind to 192.168.0.10, they just won't get anywhere, because the kernel will say, I don't know what you're talking about. There's no such address on this system. But we have a veth pair now. It's like a dangling wire. It's like I went and got a wire, an Ethernet cable, and I sort of teleported it into our host, but neither end is plugged into anything. Both ends are dangling. That means both ends can give IP addresses. So this is a kind of a bit of fun that you can play with. I can do that. And again, I can't exactly ping across it because I can't have packet D on the other end. But definitely, if you set up the right NAT rules or IP tables rules or something, you can make packets traverse this veth pair if you really wanted to. But there's no kind of reason to have this weird little wormhole in your kernel, because it's not actually it's not bypassing anything, right? It's not a wormhole through anything. It's just it's an extra step if you write all the IP tables rules to sort of plumb it into your packet flow. But I want this container to be on the network, right? So obviously the way to get things onto the network is to plug something into the bridge, because that's extending the network into our box. So I can take this veth pair and I can plug one end. As I say, veth0 and veth1 are both interfaces, so I can do to either of them individually whatever I can do to an interface. I can take veth0 and I can plug it into the bridge. Notice that it's lost its IP. It's not dangling anymore, so it can't have one. It can't be used. But veth1 is still floating around and still has an IP address. Well, this container is just a chroot on steroids, remember? It's got this isolation of many things, including the network. But what I can do is, just like I can start a process inside of it or outside of it, I can move this network interface. So I can take this dangling RJ45, because it's just a piece of software, and I can move it into the what's called the network namespace, represented by that orange box. So now I've added an extra little process you'll see on the main host, FTPD, the FTP server. It binds to addresses and serves files. It can bind to BR0. It cannot bind to veth1 because it can't see it. Ping and nginx, on the other hand, can use veth1 because they can see them. They can't use BR0, remember, but they can see that veth1. So if I then rename that interface, which is again something else I can do quite freely. You can have always been able to rename interfaces. You just normally wouldn't, because eth0 is a really good way of telling you what that interface is and what it does. As I say, E1, so it's something like EN-S0P2 is now the newer name. The kernel developers thought that was a better way to tell you what that interface is and identify it. You may or may not agree. Well, that was actually about making the names deterministic every time the things boot, because the PCI bus is now enumerated in a non-deterministic order. But anyway, I won't go into that. I can take that veth1 and I can rename it and call it eth0. It doesn't clash with the eth0 name outside, because remember the orange box isolates things. So now Ping and nginx, they know they're running on a Linux system. They know they're just Linux user space processes. And when they ask what all the interfaces are on the system, or when you run ifconfig in that container, you see something called eth0, and it's got a 172.16.02 address, and it is connected to whatever network that eth1000 network is connected to, because that that broadcast domain, that network, has been extended into our host. So yeah, in this use case, which is a very common use case, veth0 is kind of a generalization of that internal bridge port. right? It was a thing with both ends free, but a wire with both ends free isn't actually that useful. And often the first thing you do is to plug one end into a bridge. So actually, although veths are the common explanation given, and they're a good mental model, containers these days don't normally tend to use veth pairs. It turns out you can instruct the bridge, the BR0 through BRCTL, to make as many of these extra internal ports as you want, right? To make as many of these dangling yellow interfaces. So you just, every time you make a new container, you instruct it to make yet another one. So that would be, I actually don't know what it's called. It wouldn't be called BR1. I couldn't tell you what it would be called. But whatever it is called, you rename it to ETH0, and then you move it into the namespace. And that just involves like a few, that skips out a few lines of software because this is a simpler case.